Hello. Let's learn how to compute derivatives using Fourier transforms in Matlab. So to do this, I've got a program set up here. So we'll just clear variables and clear all, close all to clear out any junk that might have been lingering from previous programs. Just good practice for starting. Uh, and we'll first explore Fourier transforms a little bit within MATLAB itself, and then we'll look at derivatives. So first, let's set the domain. So for our domain, let's choose a domain of size 2 pi. Just remind ourselves that this is the length of the domain. Next, we'll choose a number of grid points, and let's just choose something low to start with. But it turns out choosing powers of 2 is kind of a sweet spot for the Fourier transform. It's most efficient when it runs on powers of 2. So we'll choose a power of 2, but something kind of small, so 16 in this case. But I'll just write it as 2 to the 4th power so we can modify that later. All right, so this is our number of grid points. And from that, we can pretty quickly get dx, so L divided by n. This is just the step size in space of our grid spacing. So, all right, from here, we can set up our grid. So let's start at 0. So we'll do 0 with integer steps of dx. So 0 up to n minus 1 times dx. That'll give us exactly n points with this dx spacing. Now, if we want to do something like start at, instead of starting our domain at 0, we want to start at negative pi, we could say add negative pi onto this. But for now, we'll just keep it here. So this is our x variable, and all of a sudden we can do some fairly simple things like let's just plot something like sine of x. So even though x is a vector, when we take sine of x, it'll take the MATLAB knows to take the sine of each vector individually. And if we run that, we see something like this. And let's emphasize it a little bit by putting something like dash star so we can see where the different points are. And in addition, let's do something like axis square, just so our axes don't get too squished in a minute. So again, nothing very remarkable. We're just seeing the points. But notice, of course, MATLAB is not actually graphing sine or anything like that. It's just graphing individual points calculated from sine and connecting them by dots. All right. So now we'd like to compute a Fourier transform. Fortunately, MATLAB handles most of this for us without much trouble. So I like to call my Fourier variables by hat, so u hat. And I'll write that as, so this, I mean, it's nice to call it u hat because it reminds you that it came from the variable u, and we're taking the Fourier transform out of it. We're taking the hat. So for that, I'll just write FFT of u. So FFT stands for Fast Fourier Transform. Technically, the transform that we're taking here is the discrete Fourier transform, or the DFT. But it's computed by an algorithm called the Fast Fourier Transform, which is an incredibly beautiful and important algorithm. But for now, we'll just use it to compute the Fourier transform. So first of all, let's see what this does. So if I run it, and let's plot it. For now, I'm just going to say plot u hat. MATLAB's autocomplete is helping me. And let's put on some of these decorations here. So we'll get this and keep the square axis. All right. So we plot this. Let me do one more thing. So we can see these plots kind of side by side. Let's do subplot 1, 2, 1 for the first one. So it's a 1 by 2 plot with the first entry. And here's another 1 by 2 plot. And this is the second entry in that plot. We plot it. We see something kind of confusing looking here on the right. So nice recognizable sign, and then the transform of it is something kind of wacky. Not only that, but it kind of looks like these are spread along the x-axis here, except for that, notice that all of that is multiplied by 10 to the minus 15. So this is a zoom in, and what we're really looking at is things that are up to machine precision only on the y-axis. So what on earth could that mean? If we take a look at what this U hat is, if I read it like this, it's kind of hard to read because it's all in columns. So what I'll do is type U hat dot prime, which will just give me the transpose. So you can use prime for a transpose, but technically that also conjugates everything. And since the Fourier transform is, can give you complex values, we don't want to conjugate those. So just a pure transform in Matlab is U hat. And so if we do that, we see this. So this is our transform of sine of x with 16 grid points. So there are 16 points again, written as complex numbers. So here's one complex number, here's another complex number. And you see the first one is 0. After that, there's an 8i, actually a negative 8i. And then we get positive 8i showing up a little bit later. And all of these other things with e to the minus 15, e to the minus 16, that's like 10 times, this number times 10 to the negative 15 or negative 16. So these numbers should be thought of as 0, right? So where on earth are these other numbers coming from, and why are they positioned that way? Well, the first thing to maybe remember is that, maybe I'll just write it here, that, let's see, I had a little cheat sheet on this. I just wanted to copy it and paste this quickly. If we have, oops, it's not letting me do that, sorry. Copy it, paste it. If we remember that sine of x can be written as, well, by Euler's identity, it's often written as 1 divided by 2i, and then minus 1 divided by 2i, with the first one times e to the ix, and the second times e to the negative ix, something like this. But if we modify it a little bit, so if I multiply by 1 divided by I, use the fact that I squared is negative 1, so 1 over I is the same as negative I, we can rewrite the thing like this. So it should have been an I. And that means that our first coefficient is negative I divided by 2, and our second coefficient is I divided by 2. Now, Matlab, when you use the FFT, it doesn't actually compute the discrete Fourier transform exactly. It computes n times the Fourier transform, where n is your number of grid points. So what we're actually seeing from the Fourier transform is that we're seeing n times this. So n times negative I over 2 is negative 8i. And the other one is 8i. Now, the reasoning for the positioning, you might say, well, wait a minute, shouldn't I see maybe some of these towards the middle or something like that? The reason for that positioning is because Matlab stores the 0th Fourier coefficient here. So for this one, the 0th coefficient is just the constant term. So if I were to put, I could put something like plus 0 times, plus 0 times e to the I times 0 times x. Up here, that's an O, sorry, that's 0. So that's the 0th Fourier coefficient, and we're seeing that show up here as 0. It stores the 0th coefficient first, then it stores the first coefficient, the one associated with e to the I times 1 times x. And in general, if we have e to the I times k times x, then those are stored, so the positive k values are stored up here all the way up to the 8th value, and then after that it loops around and starts listing the negative ones. This is because Matlab doesn't like to deal with negative indices, so we start with the positive indices first and then loop back to the negative indices showing up later. So the very last one you're seeing there is this this last index here, which is the 8i, or 16 times 2i. It's a little confusing to unpack, and if you didn't get all that, that's totally fine. We will need to think about it a little bit when we're talking about when we start taking derivatives, but for now, that's kind of what the Fourier transform looks like. And that's why we're getting this weird picture, because when we plot the thing, what Matlab's doing on the right is it's plotting all these complex numbers, and it's getting that a whole bunch of them are, say, close to their real parts are effectively zero. All right, so it turns out to be a little bit nicer to visualize this if we first take an absolute value of it. So this will take an absolute value of each of those Fourier coefficients, and maybe to be perfectly accurate, we should divide here by n, by that 16 number. So the reason Matlab doesn't do that is because when it computes, a lot of times you don't actually need the Fourier values. You're going to manipulate things in Fourier space and then transform back. And the standard algorithm to compute, or I guess a fast algorithm to compute the Fourier transform doesn't involve that multiplication by n. So they just don't do it because it would be an extra step. Just slow things down a little bit. And if you don't need the coefficients, it's okay. So here we see this a little bit more clearly. So we've got the 0th coefficient, although Matlab kind of confusingly Matlab doesn't want to index by 0. So here the index is starting at 0. So we could re-index. We haven't given these an x value, so it's just assuming that the first one is 1. But if we just count by these stars, we have the 0th coefficient is here. Then the first coefficient is at 0.5, and then we see the loop back to the original. I think that's still a little bit confusing, though. So if we use FFT shift on this, or divided by n, either way, this will just make it so that the negative indices come first. And we'll see that a little bit more symmetrically showing up here. This might be closer to what you might have expected, but the indices in the bottom are not quite right. So I'll leave it up to you if you want to plot this with the correct indices on the x-axis. But here we see a 0, and then a 1/2 indicated by the 0.5, and 1/2 here at the -1 index, and everything else is 0. So this is kind of what we would expect for the Fourier transform. I think for me, I usually visualize it just sort of individually without those dashes. Remember that these really are just points. There's no need to connect them by lines, but we see something like that. So of course, this absolute value is taking the complex modulus, the real part squared plus the imaginary part squared, and take the square root of the result. Anyway, so that's maybe a little bit too much about the Fourier transform. We won't really need all of that, but sometimes it's kind of useful to have a little bit of a picture of what's going on. In addition to that, let's see what happens if we do something like add cosine of 3 times x. So if we run it, we now see, and maybe I'll bring those spikes back so you can see it a little more clearly. We now see a few more spikes, right? So we see the spike at the 1 index, the index 2, I guess 2 and -2 here are 0. And then we have some additional spikes showing up. If we multiply this by, maybe let's multiply by 4, then it should multiply the coefficients on cosine of 4x by 4. So those should be, right, they were 1/2, so they should now be up at 2. So this is, in some sense, the picture on the left and the picture on the right contain, in some sense, the same amount of information. But this gets, I mean, the left here, it's kind of hard to tell that that's a sum of sine and a cosine. If we refine quite a bit, so let's go up to, maybe 2 to the 10th power. So that's 1,024 grid points. It happens pretty quickly. And we see this nice plot over here on the left. On the right, it's maybe a little bit harder to see, but there are 2 spikes showing up right there. So if we were to maybe zoom in a little bit on those, we have the spike showing up down here and the higher spikes. Maybe we'll try a little bit lower resolution. Let's say 2 to the 6th should look pretty good. So that's 64 grid points. And sure enough, we see a nice, trigonometric sum of 2 trig functions showing up on the left. On the right, the picture hasn't really changed, right? So we're getting a clear focus over here on the left, but that's just because it's plotting more points as we see them. On the right, we are plotting more points, but we're not really getting more information because all of these additional things are just 0. So in some sense, this can be used as a compression algorithm, right? If I want to send you this picture, I could send you a whole bunch of points, especially if I want to do it at high resolution, or I could just send you these 4 points. So, there are image compression algorithms based off Fourier transforms. Okay, so that's a little bit about how this thing is working. It's somehow encoding and storing some of the background information. Now, you might ask why I'm using sines and cosines. If I use something that's not a sine or a cosine like x, x is, we normally think about x as a very nice function, but if I continue it periodically from minus pi to pi, and then I repeat it, it gets a big jump in the middle. And that jump is very hard for the Fourier transform to capture. So if I do something like that, I get all of this sort of noise showing up here all over the place. And what's happening is that these Fourier coefficients down here are not zero, and they're not going to go to zero as the wave number goes out to infinity. So yeah, so we get a little bit of trouble with those, but anyway. So for now, we'll just stick to periodic functions. But sometimes these are kind of boring functions, I think, because their Fourier coefficients are just a few spikes. So if you want something maybe a little more exotic, you can try, for instance, e to the sine of x. This is still periodic, so it's a valid thing to take a Fourier transform of, but you get something maybe a little more interesting showing up. All right. In particular, you have the Fourier series for these. The Fourier coefficients don't go to zero. Okay, so this is enough, I think, to play with. Let's see what we can do next.